My name is Sebastian Romy, I'm from Airbus. And when we are looking to our industry, of course we have the technologies, but most importantly we have the people. And looking deeper in that dimension, I would say for me there are three most important things linked to the people in our industry. The first one is cooperation. Obviously, none of us will succeed alone. It's always a teamwork to develop a product or service, something which is changing the world. The second dimension is about inspiration. We have the privilege to live an era and to be in an industry which is making dreams possible. It's about inspiring the younger generation which are going to develop the next product with us. And the third pillar is about the transformation. Once we have a goal, when we have an ambition, we have an inspiration, it's about making it true, moving toward that dream, which brings us back to the cooperation. And actually in our industry there are very few people which are having the big marks in the field. And that's why I'm so pleased on behalf of ICAS to welcome Professor Ric Parker this morning to his general lecture. Well, I could speak for the whole time of the lecture talking about his background. Just a few dimensions for you. He joined Rolls-Royce in 1978, and his end position in Rolls-Royce was Director of the Research and Technology for the whole group, up to April 2016, when he took a well-deserved retirement, but obviously he didn't leave the arena for industry. He's a fellow. Well, he's a fellow of quite a few institutions, from the Royal Aeronautical Society, of course, from the Royal Academy of Engineering, from the Institute of Physics, and from the Institution of Mechanical Engineers. That's about the recognition we can get in this industry. He received the knighthood, CBE, the Commander of the British Empire, in 2013 for services to engineering. Everything starts by designing. He was elected CTO of the Year in Europe in 2014. And in 2015 he received the Gold Medal of the Royal Aeronautical Society. Beyond this activity, he is today the chairman of the European Union Clean Sky Research Programme. He is still an active president of ISABE. And today, as a hobby probably, he is an independent special advisor for technology strategy and technology transfer. And among his customers, which will give you a flavor of the future also. Of course, there is BP and Rolls-Royce, but there is LG Fuel Cells, and is still heavily involved in A-Star in Singapore. Without taking more time, please welcome on stage Professor Ric Parker.
So good morning, everybody. Thank you, Sebastian, for that amazing introduction. I'm flattered, and after that I can't wait to hear what I'm going to say. As Sebastian said, one of my many roles, but one of my proudest roles is as President of ISABE, the International Society of Air-Breathing Engines. ISABE and ICAS go back a very long time, 50 years, and ISABE was really the child of ICAS. It was the slightly naughty child at the time, probably, but the child that wanted to pursue propulsion with some purity. I've worked closely with your chairman, your president, Susan, and with her predecessor, our good friend Christian Marie, to bring these two closer together. We invited Susan to be our guest speaker at the ICAS conference last year in Manchester, and I'm very proud and honoured that your committee have reciprocated and invited me here today. So I'm going to talk under the heading of the future of propulsion. I've selected some items from our last Manchester conference and some of the speakers there. It was a very full agenda, so I don't pretend to do justice to the whole area, and indeed if any of the speakers are here today, don't be disappointed if I didn't pick your particular element. When we originally agreed to do this session, it was going to be a double act. I was going to talk about the future of propulsion, and then Frank Anton from Siemens was going to talk about electric propulsion. With relatively short notice, Frank decided he couldn't get to Brazil, so I've pulled together a very much personal view. I wouldn't claim it's an ISABE view, but a personal view of where I see electric propulsion going, and time allowing, I will share that with you as well. Just before I start, let me pay tribute to a very bright, very capable and very new postdoc, Ibrahim I knew I'll have trouble with that, Erilmaz of Cranfield University, who was part of our organizing committee and program committee for ISABE, and he's done a great deal of work to support me in pulling together this presentation. And if any of you are looking for a future star for your university, then without wishing to steal it from Cranfield, I can truly recommend it. So, see if the technology works. I'm going to just very briefly tell you about our conference. I'm going to talk about the future of propulsion, talking about some of the commitments we're making as an industry to support your industry as a whole, and some of the key enabling technologies. I've pulled some elements, a slide each from some of the key speakers, so we were fortunate to have some great keynotes, not least Susan herself, but also to have some very inspirational and very futuristic papers. And then, as I say, I'll produce a personal and Rolls-Royce view of electric propulsion, because if pure electric propulsion takes off, then ISABE will have to change its name, because there will no longer be air-breathing engines, so we have to get ready for that. And then I'll just get a little advertising plug for our next conference. So, ISABE last year was in Manchester in the UK, proud to host it there. It's a very, if you come from Rolls-Royce, Manchester has a very special meaning. As you see bottom left, there's a lovely brick plaque on the wall of the Midland Hotel, and this is where Sir Henry Royce and the Honourable Charles Rolls were first introduced to each other, decided to make a fantastic car at the time. And only 4 horsepower, but it was very powerful and actually very expensive car for its time, and sold very well. But then in 2015, actually after the death of Charles Rolls, Rolls-Royce got into aero engines, and they've been in aero engines ever since. So the hosts of the conference were the City of Manchester, Cranfield University, Rolls-Royce. And as you see, we had a good range of sponsors from the industry. So we had 370 registered participants, a little over 240 papers, and so not quite as big as ICAS, but since it's focused just on propulsion, and a very good representation of the propulsion community, and a very large number of keynotes. So the keynotes were interesting because we had some great people from the propulsion industry, but we wanted the airframers there. We had Boeing and Airbus telling us their view of where propulsion is going. We even had the end customer. We had a fantastic presentation from EasyJet. Actually, a very open and honest discussion about how they select the engine going forward, because obviously when they buy the A320s as they do, they have a choice of engines, and the factors they look at in making those decisions is quite an insight. And there you can see Susan on stage at the back and doing her stuff. And we had a number of interactive and parallel sessions, 248 papers, as I said, and panel discussions. And again, we made Susan work very hard. You can see her up above me here. So Susan sandwiched between myself and Richie Singh, truly a rose between two thorns. So the theme of our conference was largely based on the European Flight Path 2050. This document came out in 2012 and set the goals for our whole industry out to 2050, following on from the Vision 2020, which was getting all too close by then. And unlike Vision 2020, it did still focus on the environment, but it focused on the whole commercial side of our business, how we can make aircraft faster to market, how we can make them cheaper, how we can make more profit for the end customer. And it also focused on the customer safety and customer comfort. And these were driving themes throughout our conference, and I've used those themes to select some of the papers I'm going to discuss today. So some of the enabling technologies we discussed. Ultra-high bypass, again, a theme, some of the talks at this conference, that engines are getting bigger and bigger. How you fit them onto an aircraft is an interesting challenge. Cycle innovations, manufacturing technology, again, some interesting papers here around additive manufacturing, which is proceeding very rapidly. Virtual engine design, integrated aircraft and propulsion system, again, the days where an aircraft is a tube, two wings and two engines, apparently designed by people who've never met each other, has to change, and we must have a much more integrated approach to this whole thing if we're really going to achieve the goals for the future. And finally, as I said, I will say a little bit about the advance of electrification. And I'll be very honest, it's happening far faster than even 3 or 4 years ago I predicted. I was saying, yeah, you know, it'll happen, but little drones and some way off. But big, sizable aircraft, people-carrying aircraft, which is where I'll focus my attention, are happening with today's technology and at a rate I wouldn't have predicted even 4 or 5 years ago. So let's look at some of the invited speakers. Jerome Bonini of Safran gave an excellent talk. We're clearly very proud of the new LEAP engine from CFM, joint venture between Safran and GE, which has just been certified. Among other platforms, it's going to power the Comac 919, and a very interesting engine, a lot of novel features, in particular a carbon composite fan, woven composites, not hand layup like many of the composites, and resin infusion, so a potentially cheaper fan and significantly lighter, I think saving 500 kilograms in the total system, fan case and fan compared to a conventional engine. Also embracing other new materials, ceramic matrix composites, and embracing 3D printing. Certainly GE have invested massively in 3D printing, over $60 million in their new facility, and that's making the fuel nozzle a complex part, and the first complex part to enter routine production on an engine. And an exciting insight into the electrical world is electrical taxiing. So Safran had a joint venture activity with Honeywell. Honeywell has since pulled out, but Safran are thinking forward to use batteries or the APU and electric motors embedded in the wheels, so you don't waste a lot of fuel on the ground while you're taxiing and going out to take off. Brings with it some challenges, not least cold dwell, so to switch on your engine immediately at the end of the runway and then expect to take off and keep the engine in one piece is quite challenging, so a little more work to do there, but I'm sure it'll make it. My successor at Rolls-Royce, Paul Stein, presented on some of the interesting activities of Rolls-Royce, talking about our world-famous distributed open innovation network. So for many, many years, Rolls-Royce has not had a corporate research center. It works with universities and with the research institutes around the world, and that's been a very successful model and something we're very proud of in the company. Paul also talked about the UltraFan, a very high bypass ratio geared turbofan under development at the moment, 156-inch fan, massive fan, nearly 100,000 pounds of thrust, and the world's biggest aerospace gearbox, so over 50 megawatts, 53 megawatts of power in that gearbox. And when he spoke in Manchester, it had run for the first time in our test facility in Germany, in Dahlewitz, and run successfully up to full power. And it's since done a lot of testing, including attitude testing. So keeping the oil going around the gearbox as you maneuver the aircraft is one of the big challenges. As Paul put it, if we make this gearbox only 99.5% efficient, which would be pretty good by gearbox standards, you still have to find somewhere to hide 250 kilowatts in the oil. And that's the big challenge, is keeping the whole thing cool. And then the virtual space, increasing digital impact on our whole industry, whether in service or in MRO or in the design space. So this new design and optimization space that Rolls-Royce has created called Da Vinci, which is the new design tool for the future, with the end goal of replacing as much of the physical testing as possible by in silico testing and only doing those final tests and hopefully doing those right the first time that you need to. From Airbus, we had Charles Champion, and Charles will be joining us later today and is speaking tomorrow and also receiving a very well-deserved prize. So Charles gave an excellent talk from Airbus, some interesting projects. The aircraft you can see on the left there is a modified A340. It was sponsored by the Clean Sky program, which, as Sebastian said, I'm the chairman of, and it has the tips of the wings, the last 25% of the wing as laminar flow wings, and this is demonstrated flown with amazing amounts of instrumentation and shown the benefit of laminar flow technology. We've been talking about it for years, but this is the first sizable scale demonstration, and really is showing that about 5% fuel burn could come from laminar flow technology. I also had the pleasure of autographing this aircraft at the ELA Air Show earlier this year. It's the first time I've signed an aircraft, but wow. Rather a nice experience. We also talked about the electrical future, and Airbus is getting its mind around this at all levels. So in the bottom right, you see the personal air taxi style translation, and the previous CTO of Airbus, both previous CTOs, John Buffy and Mr. Aramenko, were very keen on these new concepts and push them forward. And then a study top right, which I'll come back to later, the E-Thrust, which is a large single-aisle aircraft for the future. 2035 needs superconducting motors and generators, but it breaks no laws of physics. It can be done and can get you a 70% fuel saving compared to a current day conventional aircraft. So a very interesting project, and again, Airbus, Rolls-Royce, Cambridge University and Cranfield University. Staying with the UK, we looked also at Cranfield University. So Cranfield have been remarkably successful. They're an all postgraduate university, so no undergraduates, focused predominantly on aerospace, and they recently won over £100 million of investment in two major new facilities, the so-called AIRC, Airbus Aerospace Integration Research Center, which is a joint center with Rolls-Royce and Airbus, looking at this whole area of integrated design, integrated systems at the physical level on the aircraft. And then the sister organization to that is the DARTEC, which is the Digital Aviation Research and Technology Center, and that again is sponsored by the industry, looking at the digital side of integration. So they've been remarkably successful and are really growing their aerospace presence. Also in the UK, and something I like to think I helped to give birth to and worked on for many years, was getting a dedicated aerospace program for the UK. That was created back in 2012. It's called the Aerospace Technologies Institute. It doesn't do any research, but it owns and manages the strategy for research in the UK for aerospace and funds that research. It has a total fund, including the matching industry money, of £2 billion, and is supporting across the whole industry, but 50% of that funding goes to propulsion. So it's a very strong supporter of propulsion research in the UK, which is also what we like to think of as one of UK's strengths. Not just the fundamental technology, but the building blocks of that, like looking forward to the future for more electric, more electronic engines and aircraft. How do you get these electronics and electrical systems to work in harsh environments, whether that's high altitude with corona discharge problems, or in high temperature environments, being able to embed motors, generators, power electronics right into the core of the engine in a temperature zone around 250 degrees C. And they've also supported a full-size facility capable of very large castings up at Sheffield University within what we call our Advanced Materials Research Centre, which can produce 1 ton of new titanium alloys. So really not just a small sample in the laboratory, but enough to make real components and prove that these alloys work. Finally, in the keynotes, again, as Sebastian mentioned, I'm chairman of the Clean Sky program, We're in our second phase, Clean Sky 2 now. We just finished, put to bed Clean Sky 1. The Clean Sky 2 is 4 billion euros of investment, again, slightly under half from the European Commission, slightly more than half from the industrial partners, and has a focus across the whole industry, regional aircraft, large aircraft, helicopters, but also propulsion. So you can see two examples there, two projects which have been very successful so far. A full-scale demonstrator by Safran of an open rotor, demonstrating in fact that the fuel saving predicted for open rotor can indeed be achieved, and that an open rotor would be 30% more fuel efficient than today's aircraft powered by conventional jet. And even if you project forward the conventional jet improvements, it will still be 5 to 10% efficient, depending on some of the installation issues. So really a great step forward for our industry. Obviously, the noise is one of the consideration factors, but it's a separate program. Also on the Clean Sky, Rolls-Royce did some testing that showed that an open rotor, modern designed open rotor, can meet Chapter 4 with a 10 dB margin. So providing noise regulation doesn't go too low, an open rotor aircraft will not necessarily be noisier than today's aircraft. So that remains to be seen. Some great work from MTU taking forward advanced versions of the geared turbofan, again in that program, and a massive program, over 800 participants, research centers, SMEs. 40% of the money and 40% of the activity is done by small to medium-sized enterprises. So let's look at some of the individual presenters. We have an excellent paper, and let's tell everybody else to switch their phone off. I've got to switch mine off. Apologies. So the first, one of our key presenters again from Honorat, a research center in France. A very nice piece of work, both experimental study and a theoretical study to back it up, looking at boundary layer ingestion. Again, that's been a theme of several papers in this conference. Looking here at the possibility of a tail-mounted engine doing boundary layer ingestion, and a very nice physical facility with a bluff body fuselage and an independently mounted power plant at the back, which can be offset to look at symmetrical boundary layer ingestion or offset boundary layer ingestion. And some interesting results both from the theory and the practice, showing a significant reduction in the engine power needed. So not only you get a win-win with this, you re-energize the boundary layer so you get more thrust and don't just create drag from the boundary layer, but also you get a reduced power needed for the engine for a given amount of thrust because of the intake of the boundary layer. And also it has a beneficial effect on the fan itself in terms of the core area pressure losses, as you can see in the bottom right graph. So really nice piece of work, and laying the scene for some of the ideas we have for the future. Another nice study and a feature of several talks, and a strong feature of yesterday's discussion in the panel around future aircraft concepts, was how you incorporate these ultra-high bypass ratio engines into future aircraft. And this study was led out of Georgia Tech by JCM Tai and others, and the team led there by Dimitri Mavris, who I know is in the audience somewhere, and also reflected in the Safran talk. So there's a minimum requirement of 9 inches, which when you're sitting in an aircraft doesn't seem very far, to be above the ground with the bottom of the, but you can already see if you look at the modern single-aisle aircraft, they're really having to flatten off the nacelle just to fit it in at all. So, you know, we're only scratching the surface in terms of the benefits of the geared turbofan. We're still at around 11:1 bypass ratio. To get the real benefits, you need to go out to 15:1, and it's very, very difficult to fit that under the modern aircraft fuselage. Some really nice studies, trade studies done by Georgia Tech. In the top 2 graphs, they looked at a conventional geared turbofan and then a geared turbofan with a variable pitch fan. The advantage of variable pitch fan is just on a propeller, like my propeller, you can feather the fan, so you actually don't need a thrust reverser. You can create negative thrust from the fan itself. That allows you to have a much slimmer nacelle. So on an underwing configuration, even adding 4 inches to the undercarriage, you still couldn't get the optimum power plant in there. With all these trade studies showed the design space was too limited. You had to take into account the effect on the LP turbine of the fan size, and also the effect of keeping roll clearance as well as this fundamental ground clearance. So you couldn't get an optimized system with a conventional underwing aircraft without a truly massive undercarriage, which would be prohibitive. But using the variable pitch fan, because you don't have the thrust reverser, because you have a thin nacelle, you can get 8 inches more fan diameter into the same space as you can with even a geared turbofan. So that was an important finding, and it set the limits for what we can do in the typical A320 or future 737 style aircraft. But really the future for these big power plants, I believe, and I know NASA has strong support of this, has to be a braced high-wing aircraft. And we heard some interesting studies on this yesterday. And that really does open up the design space, allow you to put in very large engines and fully optimize the working line. You drop the fan pressure ratio down to about 1.2 from 1.36 and get a much more efficient engine, potentially a quieter engine because you have a larger fan turning more slowly, but I'll come back to some of the challenges there later. So a very interesting and fundamental study out of Georgia Tech. Manufacturing some super work done by EOS and the University of Bundeswehr in Germany, where they produced fully instrumented guide vanes, all the instrumentation packages, all the sensors and everything, by 3D printing in a single shot guide vane. So that was really innovative use of 3D printing. And from Rolls-Royce, we looked at some fast-make technologies and new manufacturing technologies that are going to make it into the UltraFan. The bottom right is a very interesting concept from Indianapolis, Rolls-Royce in Indianapolis, called the cast bond guide vane. It's quite a complex manufacturing process, but it allows you to get the same cooling efficiency with half the cooling air. So really a huge benefit to the cycle. Any cooling air you take off from an engine, you take from the front of the engine, it's wasted to the cycle. It doesn't contribute to the thrust, it doesn't contribute to cleaning up the combustion. So to halve that cooling air for the guide vanes is really a big step forward. And again, it's a fascinating technology using electrochemical machining and diffusion bonding. So, to the virtual design space, interesting paper from AECC, the new conglomeration of the Chinese aero engine industry, forming together the previous civil engine project in Shanghai with the ISABE engine project, and taking in 2 of the major research institutes around propulsion. And they were talking about actually a very difficult problem, how you model and synthesize fan blade off and the loads throughout the whole engine on fan blade off. This is normally immensely computationally intensive. They showed an interesting substructuring result, which you could get the same result with far less computing energy and far more quickly in that case, so that was good. And then another project which is sadly all too topical is about turbine overspeed. When you fail a shaft, you hope that the turbine, not having anything driving it, will slow down nicely, but it doesn't. Under certain circumstances, it can run away in speed. So to be able to model the move backwards of the turbine and the turbine tangling, or sorry, to move forward of the turbine tangling, friction losses, and show that you can run down in an orderly fashion in the event of such a failure, rather than having an overspeed failure of the disc, which it should not be allowed, but has, as I say, sadly happened in the all too recent past. So that was a great piece of work as well, largely from Cranfield University. And we had an interesting insight into all the possible things we could do by 2050 in terms of very radically different engine designs. And there was a fascinating paper yesterday from the same European study looking at the combination of a conventional gas turbine and then a topping cycle produced by a piston engine. This is a more generic study, a reverse flow engine, common for small helicopter engines, but really unheard of in very large engines. And one of the advantages of that is it separates completely the IP and LP spool from the HP spool. So the HP spool, the shafts for the IP and LP no longer have to pass through the high temperature region of the HP spool. The temperature environment is very different. And also you isolate the HP spool from all the thrust loading of the aircraft. So again, that makes it a more benign environment and tighter clearances. So a very mechanically complex design, probably won't see its way to the market in quite that form, but it was just an experiment in putting all the goodies in one bag and really having everything you could have in a future engine, including intercooling, topping cycles, bottoming cycles. Fascinating study, and it's a really good work from a previous colleague of mine, Andrew Robbs, and his team. From MTU, we looked not at the civil space, but at future military space and what a full advanced cycle and variable cycle engine could do in that space. And I know in the US, there's been the Advent program which has pushed engines down this route as well. So an interesting study, everything that could be variable with variable compressor, which is normal, but variable turbine, variable bypass, variable mixer, and variable nozzles. So again, a mechanically complex system, but some huge prizes, particularly if you want a mission that has takeoff, fast deployment to the point of interest, but then low altitude, low speed loiter for a long time for reconnaissance or just target acquisition, and being able to optimize the engine for each of those three phases of the cycle. You can see on the left-hand three columns the sort of benefits, particularly that long time on station for loiter, nearly 10% fuel saving in that mode. When you put these engines into a conventional aircraft without doing a rubber study, you really don't get those benefits. So all the constraints back them off considerably, which is what you see on the right. So again, it just emphasizes that you have to do this as a fully integrated study, a new aircraft with a new engine concept, and keep iterating around that until you find the optimum aircraft configuration for the optimum future engine. But some really nice work from Hennig and others at MTU. And from NASA over many years at NASA Glen have done some excellent work around noise, and really they've been looking both in very good experimental facilities and in theoretical predictions at some of the future engine concepts. And while they're being driven strongly by fuel burn, NOx reduction, everything else, there's no win-win. I try to persuade the politicians of this. You cannot simultaneously minimize noise, minimize fuel burn, minimize NOx. You press one down and something else pops up. And that's exactly what this study from NASA showed, that a large turbofan, yes, turning more slowly, will be better for noise, but if the nacelles get shorter for fuel burn, then and to keep weight down, then you get more noise. Low NOx combustor tends to run much closer to the stability margins of the combustion, which again becomes a new noise source for the future. So some really good work exploring all those trades in the industry. And I think somebody said one of the papers yesterday that noise was actually the biggest source of pollution out there because of its effect on, recently discovered effect on the insect population of the world. But in America in particular, insects are declining very rapidly just because of environmental noise, confusing them and trying to mate with jet engines instead of other insects. So it's a tricky time for the insect world. Finally, and the segue to the next presentation I'm going to make is looking at turboelectric propulsion. So this is some of the NASA N+2, N+3 concepts for a fully turboelectric aircraft, and some analysis done jointly by NASA, both Glenn and other NASA institutes with Cranfield University on some of these novel configurations. Not just the technological study, but a full techno-economic study looking at different fuel systems. So how does, this is a hybrid engine, hybrid aircraft. How does it look if you're running it on hydrogen? How does it look if you're running it on kerosene? How does that compare with the best possible aircraft you could predict forward, the baseline 2035 aircraft? And some really good, interesting studies. 60% fuel saving predicted against the 2005 data. So not even then, not quite at the Akari goals of 70%, but a long way down that line. And a 10 to 20% reduction in direct operating costs. Some interesting differences between hydrogen fuel and conventional fuel. So some benefits from hydrogen fuel, but the extra tankage, the extra weight of tankage, extra volume. So liquid hydrogen is, from a mass point of view, very efficient, but from a volumetric point of view, it's 3.3 times less volumetrically efficient than kerosene. So you need very large tanks. You need pressurized tanks. So all of the papers I've spoken around are available on the ISABE website. It's one of ISABE's principles that we make all our papers freely available, not just to the conference attendees. It might be a mistake, more people might come to the conference, but we do make them free. So if you just Google ISABE 2017, it's not terribly user-friendly at the moment because it's just one big 350 megawatt file you have to download, and then everything's in there. We're trying to index it better and make it more searchable. So let me change gear and change hats. As I say, ISABE did give some thought, and you saw some papers on electric propulsion, but this is very much a personal view, drawing on some of my former colleagues in Rolls-Royce on where electric propulsion is going. I'm not going to talk about small UAVs and drones and things. A lot of other people have talked about that. I'm not even going to talk about personal transport and the air taxi. I'm looking at sizable aircraft that can carry numbers of passengers, probably 10 upwards to 200, 300. How soon will we get there, and what are the technological challenges? Electrification is all around us, whether it's in microgrids for power generation, hybrid trains, hybrid ships, and now for the future electric aircraft, in fact for now. So the EFAN-X I'll talk about in a minute, but the EFAN is already an Airbus product. It's a small aircraft, two-seater, all electrically powered, 1 hour flying time. And Airbus have learned a huge amount from doing that about how you certify an electric aircraft and what the challenges are there. So, but it's also of interest particularly to training schools which are buying these aircraft. All 4 of these areas are areas where Rolls-Royce operates, and particularly in shipping, you can see how electrification of ships has totally freed up the design space. The marine architects call it the tyranny of the shaft line. If you have to physically couple the motor to the propeller at 5 degrees running the length of the ship, it just shapes the whole ship. If you generate electricity somewhere on the deck of the ship and pipe that to an electric motor in a pod underneath the ship, you can do anything with the rest of that space. I believe if we get our minds around it, that's what aircraft will look like. So just replacing today's engine with an electric motor and generating some electricity is not the way forward. We really have to get our minds around that design space. And electrification in various time frames will touch every aspect of our industry, I believe. So the more electric aircraft, we've already seen that in the 787, a very brave aircraft where almost everything that can be done electrically is done electrically. The only hydraulic system, even then it's electro-hydraulic, is the landing gear. Every other system on that aircraft is electric. And again, a very brave step for Boeing, a very good step forward. But we'll see that in the military world as well. We'll see personal mobility there. In fact, Aston Martin at Farnborough Airshow just recently unveiled their flying car of the future, which got a lot of attention. That's not it, that's an Airbus image. Hybrid turboprop, You see there the Aurora concept aircraft that was funded by DARPA has been put on hold at the moment. I'm sure that concept will come back because it's a great idea, a full swing wing, vertical lift, and horizontal flight aircraft. And out to the future with hybrid turboprops. So some of the challenges we face and some of the benefits. So efficiency of, depends where you start your calculation of efficiency. If somewhere on the ground you're burning ground coal to generate electricity to charge batteries, that's probably not the best starting point for the electric aircraft of the future. If you either have a hybrid aircraft that can generate enough electricity itself to always land with the batteries fully charged, that's a great step forward. If you charge it on the ground using nuclear energy or solar energy, that's also a great step forward. It's going to, again, affect the whole capability of the aircraft. You're going to be able to do things you can't do today. You're going to have more redundancy potentially with distributed propulsion. So electric aircraft could actually be safer than conventional aircraft. And some of the studies we've done with a single power plant with 6 fans and a big battery. So you know, the single point failure modes just don't exist. You can always get to a safe point of landing. As the military pilot always used to say, the advantage of being in a 2-engine aircraft is that when one engine fails, you know you have just enough power to get to the scene of the crash, which is not the idea. So in emissions, again, 0 or very much lower emissions, and even the hybrid aircraft can get to 60% less fuel burn, therefore 60% CO2. And as I say, increased safety, increased redundancy. There are some challenges, and that is the rate of progress of electrical technology itself. So projecting out to the future, the sort of batteries that are in electric cars today are at best 200 or 170 watt-hours per kilogram. The best predictions of where that's going to get to in the next 20-odd years is out to 500 watt-hours per kilogram. You've got to be very careful here. People quote amazing figures, but they're talking about cell. They're not talking about a complete battery, including the casing, the cooling system, the charging system. When you put all that in there, it gets a lot heavier. And even at that size of 500 watt-hours per kilogram, for a 737, A320 size aircraft, the batteries, if it was all electric, would be 3 times the current payload of the aircraft. So you couldn't fly that aircraft all electrically, even at that point in time. So it's going to have to be hybrid. But other things have to keep up with the power electronics. We did a study in Rolls-Royce back in 2005, the power optimized aircraft. The power electronics were 2 American refrigerator-sized boxes full of electronics. And when I said to the designers, hey, that's got to fit in a shoebox, you know, they looked at me as if I was crazy. And the motors and generators are going to have to accelerate as well. So the motor industry will not take this far enough. When they stop, when it's good enough for motor, it will still not be good enough for flight. But as I'll show you, even with today's technology, it's still possible to do some interesting things. So electricity could affect our industry in 2 ways. It could be incremental, just more electric aircraft, electrically enhanced aircraft, so doing boundary layer ingestion electrically rather than using the fuel motors. Or it could be totally disruptive, and disruptive not just in the style and nature of the aircraft, but possibly in the whole industry. It may allow new entrants. It may mean that the electrical technology becomes the important technology, and some of the other things we depend on for a living are somehow secondary technologies. So we have to certainly keep an eye on that, and all the big players, whether it's Airbus, Boeing, or the engine makers, are acutely aware that it's both an opportunity and a threat, and unless they get on top of it, then we'll see new entrants coming in. In transport, then, it can affect both short and medium range aircraft, both at the personal mobility level. Again, the Aurora concept in the middle there, and an aircraft at the bottom with boundary layer ingestion from an electric fan on the back end. And it could change the whole nature of short-range air transport. So, you know, the airport of the future may just have aircraft that are traveling 100 kilometers, a few hundred kilometers. Journeys today you would do by car or train. But it could be feasible that the electric aircraft may open up that whole space for more people to use air transport. And it becomes very valuable in certain countries. I know Norway is taking this very seriously, even to do what on the map looks like a very short journey between two towns. When you put in all the fields in between, you finish up driving for 200 miles where you can fly for 50 miles. So this really is exciting some countries more than others, and exciting developing countries that haven't yet invested in the rail or road infrastructure and can just bypass that whole phase in life. You know, it must be much cheaper to put down 2 by 1 kilometer of runway than to build 1,000 kilometers of road or rail. You know, and that's the trade people can't get their mind around. But if that world's going to work, and it's not just the technology that has to change, the whole way we use airports, use air travel has to change, security has to change. We cannot, if you're going to take a half-hour journey by aircraft, you don't want to arrive in the airport 2 hours before, you don't be waiting half an hour to get your bags back. So the whole airport infrastructure has to move with it and change. That will probably mean more personal screening, more pre-authorization for security and all this. Or somebody did propose in one of the studies we did that everybody should just fly naked, then it'd be obvious they weren't hiding anything, so you wouldn't waste all this time taking off your shoes and boots and that. But, it wasn't a pleasant concept, was it? So it'll be progressive. The more electric aircraft today and the more electric engine is already here. We're starting to see systems that are conventionally hydraulically driven or driven by pressurized air or driven by physical drives being replaced by electrical systems, fuel pumps, oil pumps, all the rest of it driven electronically, and as I say, all the actuation on the aircraft. But then you move on to systems that the prime systems start to be electrically driven, then you add in power storage, and that gives you a whole new dimension to it. And finally we'll get to the all-electric or hybrid electric systems of the future through these stepping stones, and that's just a personal view of the order in which they'll happen. So let's just look at some of the concepts we could be seeing. This is an interesting study, a tail-mounted electrical propulsor re-energizing the boundary layer, providing additional thrust and removing drag. So, as I said earlier, a double benefit, and embedded using the conventional engines for power generation. So on the 787, we're already seeing engines that have to deliver 0.5 megawatt of electricity for that 270-seat aircraft. It's not a big jump to say, well, let's generate 1 megawatt or 2 megawatts of power from the engines and use that to power this aft fan that can suck down the boundary layer. Another project I think is very interesting because, as I say, it's not breaking any boundaries, it's not waiting for future technologies, is the Zunum Aero aircraft. This is a 12 to 19-seat, relatively short range, 700-mile aircraft, a couple of megawatts of power. And actually, I've done the sums, it seems to wash its face. It's a hybrid system, it doesn't rely on fully recharging the batteries during flight, so you either have to wait at the far end, which if you're doing a 700-mile commuter journey and flying home in the evening is not a hardship, or actually it's designed so you can drop out the batteries and put in new fully charged batteries. But a ton of batteries gives you a ton of fuel savings, so it washes its face. Yes, the electrical system and the generator adds extra weight, but it probably takes out a couple of passengers worth, that's about it. So it does look exciting. They're predicting 2022. I think that's a bit adventurous, but it's certainly coming very soon, and as I say, it doesn't break any bounds in terms of technology. A slightly larger scale demonstrator, the EFAN-X. This is Rolls-Royce, Airbus, and Siemens working together, taking a BA-146 aircraft, just happened to be a convenient small 4-engine aircraft, so having one power plant that's totally new and 3 usable old-fashioned ones gave the pilots a bit more comfort, and that's an A2100 power plant generating electricity around 2 megawatts. Another 2 megawatts of power potentially coming from the battery in this series hybrid system and replacing one of the conventional motors with an electric motor, and again due to fly around 2020, 2021, so well on its way, but only a demonstrator of this phase, but a demonstrator of an aircraft that could be an 80 or 90 seat aircraft. And then we come to ICAS, as I say, Cambridge University, Cranfield University, Airbus, Rolls-Royce. Really, this did push the bounds in terms of technology. It didn't break any laws of physics, but the motors had to be superconducting, the cables had to be superconducting, the generator system had to be superconducting. And 6 embedded fans, all, as I say, superconducting electric motors. A single gas turbine power plant, but still, and Sebastian did some good work helping us realize that the safety factors could be met from this concept, so thank you for your assistance in that. And an exciting concept. Will it be here this side of 2035? I doubt it, but nonetheless, as I say, it sets the goalpost, but it still won't be an all-electric aircraft of that size even by then. So for the young people present, if you want some technical challenges, these are the things to go after: the safety and certifications, cooling, control, even simple things like connectors. So you make your battery packs for the future small and compact, your generator small and compact, and then industry standard connectors for a couple of megawatts of power are huge. You finish up with a connector block and plugs and wires that are the same weight as these nice compact generators you've just designed. So everything's got to change. You can't just do the main building blocks. If you still have heavy copper wires linking these things together and big chunky connectors that people can get on and off in a cold morning with their gloves on, then life is not going to get there. I think we need fault-tolerant systems. We need ultra-safe systems. I don't think we're going to see radically different battery chemistries in the next 10 years. Lithium-ion was developed back in 1982. It's only just making its way into service now, and as we've seen, it does have its challenges for aero use. So the big challenge short-term is how you make lithium-ion safe, reliable, and how you control better the charging, discharging at altitude in the air to work better. So a lot of challenges out there for the young people to go after. I'd encourage you all to do that. I believe the future is electric, so get in early and get on with that. And if you'll allow me just a plug for our next conference, we're down in Canberra next September, and I'd like to see as many of you there as possible, and we'll certainly be inviting your president to come and give their view of the world going forward. So thank you all for your attention and your time, and enjoy the rest of the conference. Thank you.